Good afternoon, good morning, good evening. Hello, everybody. Thank you very much for joining us today on this webinar with Hamamatsu and optics.org. I'm here with Sara Ziliani, and we will be giving you a short presentation on assessing food quality and safety with SWIR and X-ray inspection techniques. Hi there, Sara.
Hi, Rob.
I would like to make a point of introducing Sara first of all. Sara has a PhD with Sales Engineering Industrial Hamamatsu Photonics Italy. Sara has been with Hamamatsu Photonics Italy since the beginning of 2022, and she is responsible for industrial X-ray, NDT spectroscopy and radiation monitoring markets. Prior to working at Hamamatsu, Sara completed a PhD in nuclear physics with a project on gamma ray spectroscopy and radiation detectors. So what I'm going to do first of all is give everyone a few sort of house rules with regards to this afternoon's webinar. We have a chat box in your dashboard. If you have any questions for Sara throughout the presentation, please pop those questions into the chat box, and what we'll do is try and get through as many of those in the Q&A session at the end. If for any reason we don't get through to your question, don't worry, someone from Hamamatsu will be contacting you directly to answer any questions that you may have presented. This webinar is also being recorded, so if you have to drop away, or if you can't get to the end of the presentation, or indeed you want to watch it again, you will be able to catch it on the optics.org website in about 24 hours. Okay, what I'm going to do is thanks Sara again for giving today's presentation. I'm going to turn my camera and mic off, and then Sara, it is over to you. Thank you very much.
Thank you. So good evening, everyone. And thank you, Robert, for the introduction. And thanks to optics.org for hosting this webinar. So on behalf of Hamamatsu Photonics, I am really glad to take you on this journey about food inspection with different techniques. On one hand, I will show you some insights on shortwave infrared techniques. And on the other side, we will dive into X-ray inspection. So let's start with a quick overview of this presentation outline. I will shortly give you a brief introduction of Hamamatsu Photonics company before giving you some information about why we would like to inspect food. Then we will enter into the technical details of different food inspection techniques, namely shortwave infrared imaging and spectroscopy. And after that, we will go into the details of X-ray imaging. So for those who do not know us yet, Hamamatsu Photonics is a Japanese company with headquarters in Hamamatsu City in Japan, who manufactures optoelectronics components and systems since 1953. In the first 71 years of the company, we grew to around 6,000 employees. And one of the most remarkable points of our company is that we provide more than 15,000 products in our portfolio. All these products are used in a large variety of applications. In particular, they are employed in academics research and high energy physics projects, but we are also present in the pharmaceutical, medical market, passing through automotive, industrial machinery. And today, what we are going to discuss is the food manufacturing applications. So let's start with a fundamental question: why we would like to inspect food? So let's take a look at the growth of the population during the last decades. In the last 70 years, the world population has grown from 2.5 billion people, reaching 8 billion people in 2023, and we expect to exceed 9 billion people by 2050. So this point alone makes you understand that the need for safe food and high quality food should grow in the future. However, it is difficult to find qualified personnel there are difficulties and a crisis in the supply chain. And in addition, there are conflicts all over the world. And all these factors complicate the situation. So in this context, providing sustainable and safe food, it's a crucial point. So introducing an automatization of the entire food supply chain and introducing machine vision for early inspection can create safer food on one side and produce less waste of resources on the other side. Here we will discuss the introduction of optical inspection. And now that we understood why introducing this type of inspection and why to inspect food is so important, we can go into the details of the different techniques available and how to realize and introduce these techniques in the food supply chain. So the first ingredient for optical inspection is the light. The visible light, the one that we can see with our bare eyes, it's just a tiny, tiny portion of the entire electromagnetic spectrum. In general, electromagnetic spectrum has different properties based on the energy that the light carries. In particular, if we go to the lower side, to the lower energy side of the electromagnetic spectrum, we encounter radio waves that are the waves that allow us listening to our favorite music while driving on our cars. On the opposite side of the electromagnetic spectrum, where we have higher energy, we encounter instead gamma rays that are emitted, for example, during radioactive decays in a nuclear reactor. So you see there are complete different behaviors if we go at the opposite sides of the electromagnetic spectrum. If we take a look in the intermediate part of the electromagnetic spectrum, we have the infrared light. It is conveniently subdivided into near infrared, short wave infrared, medium wave infrared, and long wave infrared light. Depending on the wavelength, so from 0.75 to 1 microns, we have near infrared. From 1 to 2.7, we have short wave infrared, and so on. Today, what we are going to do is to concentrate first on the short wave infrared light, and second, we will take a look at how X-rays work. So we can start with shortwave infrared imaging and spectroscopy techniques. Let's start with a parallel with visible light. Let's take a look at an apple. If we look at this apple with our own bare eyes, we can see the color, we can see the shape and the size. But if we move to shortwave infrared range, we lose the color information. However, we gain additional data that are not present in the visible range. In particular, we can detect moisture, we can observe and detect foreign objects, and observe, for example, we can observe defects just below the surface. So we can see below and beyond some types of surfaces. In the visible range, we can see the light with our own eyes, but in machine vision, the eye is substituted by an image sensor. In particular, the sensor is usually made of silicon. In the shortwave infrared range, instead, we have a different type of sensor. It is not made of silicon, but it is usually made of a compound of indium, gallium, and arsenide, which I will call here in short InGaAs. This type of technology, the shortwave infrared, can be applied to agricultural sorting. So, for example, to look for bruises on fruit, but also to sort, for example, white rice or coffee beans from stones of the same color that are not detectable in the visible range. However, we do not only apply this type of technology to raw products, but also to packaged food. In particular, since you can see through some types of surfaces, we can count the quantity of products inside a package. We can check the integrity of the food inside the package. But we can also check the filling levels, or we can check the liquid leakage from package closures. Hamamatsu Photonics provides a wide range of products for this type of application. In particular, we have sensors, pair sensors, both one-dimensional and two-dimensional sensors that cover the range of shortwave infrared up to 2.5 microns and feature a low noise. These sensors are very useful for those who would like to build their own X-ray cameras, their own shortwave infrared cameras, but of course, it's not always very useful. So we provide not only sensors, but also modules which integrate the sensors together with electronics and a mechanic, like the housing and the lens mount. But we can also provide ready-to-use cameras that, in addition to the housing and the lens mount and the electronics, provide also calibration functions that are not present in the modules. What I would like to underline is that we have a brand new InGaAs camera, a two-dimensional camera, which covers not only the shortwave infrared range, but also the visible range from 400 nanometers up to 1.7 microns. So up to now, I talked to you about imaging with shortwave infrared. But imaging, it is not the only technology available in the shortwave infrared. We have also spectroscopy. Spectroscopy is a technique in which the light is separated into its components of the spectrum. And for each component, we measure its intensity. For example, with an image sensor. With this type of technology, we can extract chemical information on the food that we are inspecting. So we can extract information about nutrients and ripeness of fruit. And we can assess the quality of the food based on molecular information. Hamamatsu Photonics provides also for this application a large variety of products. In particular, we provide mini spectrometers because they are very, very small, like these ones that you see are of the size of a coin. And we can provide components that should be integrated inside devices, or we can provide ready-to-use devices that can be connected directly to a computer. I will not enter into many details of the spectrometers, but I will show you two products which are quite interesting for this type of application. The two products I would like to show you today are a Fourier transform infrared spectrometer, or in short, FTIR engine, and a spectrometer based on the Fabry-Perot interferometer, or in short, FBI. Both of them measure the spectrum of the shortwave infrared light. And you can see here they are very, very compact. For example, the FTIR just stays in the palm of your hand, while the FBI weighs only 5 grams. Both of them give as output a graph of the light intensity as a function of the wavelength, or the absorbance of light as a function of the wavelength. In particular, in this graph here, you can see that there are some peaks associated to the absorption of specific constituents of the food we are inspecting. In particular, here we are measuring the presence of alcohol in different beverages. We can, regarding FPI, we can provide not only the ready-to-use module, which can be directly connected to the PC, but we can also provide the component that can be installed inline or inside the device. Regarding the FTIR engine, instead we can provide also the lamp, the halogen light, a broadband light that can be used together with this product. Both of FTIR and FPI cover the shortwave infrared. FTIR has a much larger range, between 1.1 and 2.5 microns, while for FPI, there are 3 models covering 3 regions in shortwave infrared, around a few hundred nanometers. What I would like to underline is that these products are particularly useful to prevent fraud in the production of food, especially olive oil, wine, coffee, and honey. Okay, so we considered imaging and spectroscopy as separated technologies, but what happens if we put them together? What we obtain is the so-called hyperspectral imaging, where the spatial and spectral information is collected at the same time. So here on the right, you see the concept behind the realization of a hyperspectral imaging camera. So you have a 2-dimensional sensor. On one axis, you measure the spatial information, while on the other axis, you decompose the light into its components, and you measure the spectrum. The spatial and spectral information are collected at the same time. Hamamatsu Photonics can provide sensors and modules to realize your own hyperspectral camera once coupled to a suitable optics. In particular, we have a complete range of InGaAs sensors that cover from 1 to 2.5 microns, and they feature a low readout and dark noise and a high-speed response. And these modules and InGaAs sensors can be used in all the applications that I mentioned before, so food chemical composition measuring, food sorting, product ripeness, and so on. Okay, this is all for the shortwave infrared part. Let's dive into the technical details of the X-ray imaging. But before entering the details, I would just like to take a short historical detour. X-rays were discovered on the 8th of November 1895 by Wilhelm Röntgen, the guy that you see here. Röntgen was a researcher, a German researcher, particularly meticulous and really, really expert in experimental experiments. And during one of his experiments investigating the cathode rays, he realized that close to its setup, there was a screen containing barium that was slightly shining. So what he did was just putting his hand on the trajectory of the hypothetical invisible rays, and what he saw were the shadows of his bones. So what he did at that moment, he tried to change the material of the screen until he found out something that could capture the image. So he just called his wife Bertha, and he asked her to keep her hand still on a photographic sheet. And after 15 minutes, this is what they obtained: the first radiography of history, where you can see the wedding ring of Bertha. The discovery was really shocking, and in few months, Röntgen and his discovery were on all scientific magazines of that time, and everyone understood that his discovery was really crucial for the medical field. And for his incredible discovery, he was rightfully awarded the first Nobel Prize for Physics in history in 1901. And I probably believe everyone who is listening to this webinar has been X-rayed during his life. So let's come back to the technical details. How X-rays work. Let's take an X-ray emitter. We have X-rays emitted from the source. When they encounter an object, X-rays can be transmitted, absorbed, or scattered. The quantity of X-rays transmitted and absorbed in the material depends on the properties of the material, namely the density, the thickness, but also the atomic number. And measuring the transmitted X-rays, what we can obtain is exactly an X-ray image or a radiography. So in principle, we can X-ray everything, but today we will concentrate on the food inspection, where you can find contaminants inside of products that can be harmful for the final consumer. In modern systems, we do not use photographic sheets anymore, like in a Röntgen experiment, but this is what our modern system looks like. We have an X-ray source. We have an object that usually moves on a conveyor, which is a typical case for food during the production phase. And on the other side, we have an X-ray line scan camera. With this setup, we can inspect food. And for example, we can look for rotten parts inside food. We can check the quantity of products inside a package. But most important, we can look for contaminants in both raw food and in packaged food. This is the most simple system that you can realize, but sometimes it is not enough. Sometimes the objects are overlapping. Sometimes the contaminants are too similar to the product that you are inspecting, so they are very difficult to be detected. In these cases, what we can do is to introduce the so-called dual energy X-ray imaging. The setup is almost the same. We still have an X-ray source, the moving object, and the X-ray camera. But in this case, inside the camera, instead of having a single sensor that reads all the X-rays that arrive on the camera, we have two sensors separated by a filter. The first sensor measures the low energy X-rays, while the second sensor measures the high energy X-rays that manage to pass through the first sensor and the filter. So in this case, we obtain not a single image, but two images, one for the low energy X-rays and one for the high energy X-rays. And combining these two images, we can reach a higher detectability rather than the single energy, and we can identify thin and low density contaminants. Here is an example. We have a package with gummies inside and rubber balls that are the contaminants to be detected. So with single energy, what we obtain is that the overlapping gummies are misinterpreted as contaminants, while the rubber balls are not even detected as contaminants. On the other side, with dual energy, the overlapping gummies are not interpreted as contaminants anymore, while the rubber balls are rightfully detected as contaminants. Hamamatsu Photonics can provide both single energy and dual energy cameras. Both of them have a 0.4 millimeter pixel size, and they are available with selectable detection width. In particular, the single energy cameras are available up to around 1 meter of detection width. Single energy cameras are available also with the low energy compatible option to detect very thin products like tea bags, while dual energy cameras are usually used to detect bones and fish bones inside, for example, poultry or fish. Regarding dual energy, again, we do not provide only the hardware, the camera itself, but we can also provide the software. The software is called a dual extracts, and it features a new computing technology, new generation computing technology that efficiently combines the low energy and high energy images to obtain a single image to enhance the detection of contaminants in line. I mentioned you before that for the single energy line scan cameras, there are some models which are compatible with low energy X-rays, but that's not all. Hamamatsu Photonics can provide also an X-ray source with a fixed voltage of 15 kilovolts, so low energy X-rays, and a tube current of 1 milliamp. I must admit, this is one of my favorite products because, it's really, really compact. It stays on the palm of your hand. It's really simple to be integrated in a system because it does not require heavy and complicated shielding. You can use simply 10 millimeters of PVC to shield from the X-rays emitted from the source. And it forms a very nice couple with together with the X-ray line scan camera compatible with low energy. And in general, the message I would like to pass you is that with lower energy, there is a cost reduction for the production of the machine because you do not need any heavy lead shielding. As an application for the the low energy X-ray source that I showed you in the previous slide, we can inspect gummies again. For example, we can find contaminants like metallic balls here. We can inspect for packaging defects, excess plastic in the package, or we can find organic contaminants like these wonderful insects in the package here on the right. So this is also all for the X-ray part. Let's put everything together and take a look at the comparison between shortwave infrared and X-ray technologies. Let's come back to the original Apple example. In the visible range, we can see the color, the shape, the size of the apple, and in this case, we see that it is perfectly fine. There are no external defects. However, with visible light, we cannot identify defects that are just below the surface, just below the skin, and we cannot see any contaminants inside the apple. If we look at the shortwave infrared image, what we actually see is that there are some bruises just below the surface of the apple, and there are some defects of the skin. However, with shortwave infrared light, we still cannot see defects inside the apple. To do so, X-rays come to our aid. X-rays pass through the apple, and we can see contaminants inside, like this metallic wire. So, if you are still up to now, we understood how these type of technologies compare, but let's get into more details. X-rays, both X-rays and shortwave infrared can see beyond the surface to some extent, because shortwave infrared, for example, cannot see through metals, while X-rays can be used to see through metal, for example, metal cans. However, X-rays are not performant in looking for superficial defects, while shortwave infrared are much better to look for this type of defects. Regarding the type of information that X-rays and shortwave infrared provide, they are different because X-rays are more focused on the quantity and thickness and density of the product, while the shortwave infrared are more concentrated on the chemical composition of the product. Regarding the practical realization of the machine, X-rays usually need shielding, and except for the 15 kilovolts X-ray source I showed you before, they usually are quite heavy and made of lead, while the shortwave infrared usually do not require shielding. So overall, the X-rays are expected to be much expensive than shortwave infrared, especially for the shielding part, because you have to comply for safety regulations. So if you are still unsure on which is the best solution for you, I suggest you to try it. Of course, you do not need to purchase an entire X-ray source and detector or shortwave infrared cameras for the tests. As Hamamatsu Photonics, we can provide you demo units together with all the accessories needed for your tests. And specifically for X-rays, if you do not have a shielded machine or a shielded room to test them, in our European offices, we have specialized facilities where you can carry out your tests together with us. So we are almost at the end of this presentation. I would just like to give you a glimpse of the future. We are going to present very soon a new technology based on artificial intelligence and X-ray simulations to remove the background noise of X-ray images. So please stay tuned for this new technology and for the new products that Hamamatsu always provide. I would like to, I hope you enjoyed the presentation, and I would really like to thank you everyone for being present and for your attention. I am now available for your questions.
Thank you, Sara. That was incredibly insightful. I learned an awful lot. So thank you very much for running through not only the applications for both SWIR and X-ray cameras and some components, but also a little bit about the history as well, which is fascinating. We do have a few questions which have come in. So if you don't mind, I'm going to run through some of those questions. Please feel free, if you have any questions that come to mind, to pop those into the chat box, and we will get through as many of those as we possibly can. One thing that did spring out to me was that you talked about the two different technologies in isolation, but can they actually work together in sort of partnership, you know, if you've got a sort of machine vision system?
Yeah, so in principle, you can put both of these techniques in the same production line, but usually they are not put inside the same exact machine, because of course the X-rays should stay isolated from the outside world. So usually they can be put together on the same production and inspection line, but not exactly in the same machine.
Right. Okay. And I guess that kind of moves on to one of the other questions we've actually had here, thinking about production lines and sort of how you actually build those production lines and the functionality. And so, I mean, what is the smallest products that you could probably see with this particular technology?
Okay, so first of all, it depends on the type of technology. It is different between shortwave infrared and X-rays. With shortwave infrared, it depends on the resolution of the camera itself and on the optics, so the zoom that you have in your system. Regarding the X-rays instead, you do not have optics. You cannot bend light when you are talking about X-rays. X-rays just move in a straight line. So usually it depends on the geometrical magnification, because when you have an X-ray source and a detector, the product as projected on the detector. So you see the product as a shadow on the detector. So it is magnified, and the magnification depends on the distance between the X-ray source and the product, and between the X-ray source and the detector. And of course, the final detection capability depends on the pixel size of the camera and combined with the magnification of the object.
Okay, so it's really about bringing those systems together.
Yes, it's a geometrical magnification, which is quite simple to understand because it's just a shadow. And of course, on the other side, once you have the shadow, you have to take into account the size of the pixel of the camera.
Okay. Now we looked at sort of a lot of the SWIR applications looking at packaging. Can SWIR technologies, can that see through all types of plastics?
The answer is, in general, no. Shortwave infrared can see through some types of plastics, but it depends not only on the type of plastic, but also on the thickness of the plastic. So if you have a very thick plastic, it's usually very difficult to see through it using shortwave infrared, even if it is a quite transparent plastic. While if you have a thin one, it depends on the type of plastic.
Okay. And again, sticking with food packaging as an application here, are X-rays actually safe to use on food?
Yeah, absolutely, yes. There are some studies in literature in which food has been exposed not only to X-rays, but also to gamma rays, which are much more energetic, as I explained to you before. They didn't see any type of transmutation of food. So X-rays are completely safe to be used on food, provided that the personnel who is using the inspection machine is protected. So the machines should feature the right shielding and usually comply to radiation protection regulations. So once the machine is safe, it's perfectly safe to irradiate food with X-rays.
Okay, excellent. We've got a sort of relatively detailed question here, which is, which detector do you recommend using the low voltage source, the 15 kV to 25 kV, was specified as a minimum threshold for detectors?
Yes, so the detector is usually composed of a sensor, a scintillation material, which converts the X-rays in visible light that is seen from the sensor, and on top of it, there is a window. So usually, the low energy compatible sensors have a different type of window and usually have a carbon made window that lets the X-rays pass through. If the window is thick or if it is made of a heavy material, it usually blocks the low energy X-rays. Therefore, we have specific types of detectors with a specific type of window that let the lower energy X-rays pass through.
Okay, thank you. And whilst we're talking about sort of penetrations and things like that, taking, as you had the example of an apple, how deep will SWIR radiation penetrate? Is it a couple of millimeters? Is it setup dependent? You know, how far can it actually penetrate?
Yeah, so it usually penetrates just the skin. So you can see just below the skin. So I would say less than a few millimeters.
Okay.
And of course, it depends on the intensity of the light. If you have a very, very powerful light, it can penetrate more. But usually it cannot pass through the entire apple.
Right. Okay. And you highlighted some of the product ranges you've got there. Does Hamamatsu have any detectors that capture both the visible and the SWIR light?
Yes. So I showed you before our brand new camera. This specific camera captures both visible and shortwave infrared light. The sensor is sensitive from 400 nanometers, which is in the visible light, and is sensitive up to 1.7 microns. So it covers all the visible light, the near infrared, and the shortwave infrared, up to 1.7 microns. So this one, for example, is a very peculiar product that covers both the ranges.
Okay.
Of course, we have also cameras in the visible range alone, but probably they are not perfect for food inspection. They are more easily used in life science and research projects where you have very, very little light.
Okay. You've got a very complimentary one here, which is a beautiful presentation. I would like to know if Hamamatsu offers some solutions for automated detection.
Yeah, so all our cameras can be connected to a PC, and we usually provide an SDK where you can integrate your the camera into your environment. Once you have done this, you can usually the customer realizes its own automatic detection of defects, and it can even be even based on artificial intelligence if you're able to realize it. So in principle, all our cameras can be part of an automated detection system, but we do not usually provide the software that identifies the defects automatically, because there are many different applications. Even in food inspection, we can have agricultural sorting, we can have raw food inspection, we have packaged food, and the contaminants are very different one from the other. So the automatic identification of defects should be tailored on the customer needs. So it is better if the customer realizes its own software for the automatic detection.
Sure. And I'd imagine that's part of a consultational process between sort of
Absolutely.
yourselves. Yeah.
Absolutely, yes. We usually try to understand as much details of the customer application as possible to provide the best solution for them. And in case you have some requests for a customized product, we can also do it.
Okay. We have another one here, which is also very complimentary. So nice presentation, Sara. Thank you. I cannot remember if you told the energy range of dual detector, low and high ranges can be tuned according to specific applications.
Yeah, so they usually arrive up to 160 kilovolts. The lower energy depends also on the distance between the X-ray source and the detector. It is usually around 25 kilovolts, and it depends on the application, because what we would like to obtain finally is the contrast in the image between the actual product and the contaminant. So we should try multiple energies to see multiple energies and multiple currents to see which one is the best. So in principle, between 25 kilovolts and 160 kilovolts.
Okay, we've probably got time for one or two more questions, if that's all right. So
Absolutely.
We've got one here. What about the X-ray source size role in affecting image resolution? Is it a point source, focal point?
Yes. So in regarding the resolution that you obtain on the detector, of course, it depends on the focal spot of the X-ray source. So for those who are not used to talk about X-ray sources, the focal spot is the point where the X-rays are emitted, and the effect of the size of the focal spot is to introduce eventually a blur in the final image. So if you have a point-like source, a point-like focal spot, you finally obtain a very sharp image. If you have a non-point-like focal spot, multiple points of the focal spot can intercept the same point on the product and then arrive on the sensor. So what you obtain is the actual image of the product and then a halo around due to this effect. So the X-ray source focal spot usually is involved in the final resolution that you obtain. What I can tell you is that in food inspection, the focal spot required is not usually so big, so small. Sorry. For example, between 0.4 and 0.8 millimeters of the focal spot of the X-ray source are usually sufficient. I can tell you that Hamamatsu Photonics is specialized instead on microfocus X-ray sources, where the focal spot is very tiny, about few microns, but it is not the food inspection is not the killer application for this type of X-ray sources.
Okay, thank you. I guess I have a question from me as well. Is there going to be different shows that we can see Hamamatsu in person? Is there anything coming up between now and the end of the year where anyone that's at this presentation, can come along and actually speak to someone in person?
Absolutely. So we have a few exhibitions where you can meet us in person all across Europe. We have one in UK at the beginning of September, one in Denmark, and one in Sweden in October, and one in Italy at the beginning of November. So you can come and have a talk with us to understand if our technologies are suitable for your application, and meet us in person, of course.
Excellent. Okay. Well, I think we have just about run out of time. I will say to all our attendees, thank you so much for joining us this afternoon or this evening or this morning, wherever you may be. This presentation will absolutely be shared on the optics.org website. You can see it all again within the next 24 hours or so. You can reach out to myself or Sara directly if you'd like an actual copy of the presentation. I'm sure that's okay. And we can get that arranged for you too. If you have found this webinar particularly interesting, you can find lots more other information about SWIR and X-ray technologies on the optics.org website. We will be making sure that Sara and the team at Hamamatsu has all the information from you guys. So if you want to reach out to them directly, you'll be able to do that with a follow-up email you'll get in the next 24 hours. And likewise, you can pop along and see them at one of the shows coming up later on this year. Sara, it just remains for me to say thank you so much for an excellent presentation. Thank you again to Hamamatsu. And I look forward to seeing all of you guys very soon in the not too distant future. Have a great rest of your day. Thank you.
Thank you again, and goodbye.
Bye-bye.